Hello, I'm Jonathan Thorpe from Sony Europe, and welcome to this presentation on what's new in NMOS CPP. Firstly, I'm going to explain what NMOS CPP is for those who don't know. And next, I'll give a brief overview of the recent additions to the software. I'll then go into some detail about those recent additions, namely our implementation of the NMOS Authorization and Security specifications, and the NMOS control specifications. What is NMOS CPP? NMOS CPP is Sony's open source implementation of the Networked Media Open specifications in C++ and is licensed under the Apache 2 license. NMOS CPP is a library that can be used to implement NMOS registries and NMOS nodes. In the open source code, you will find an example registry application and an example node application. All of the NMOS specifications are either already implemented in NMOS CPP or currently under development. In fact, we can see here all the NMOS specifications that have been implemented so far in NMOS CPP. And our aim is to keep the NMOS CPP code up to date with the latest AMWA NMOS specifications. So what's new in NMOS CPP? Recent additions to the code are our implementation of the IS-10 NMOS authorization specifications. This includes the practices specified in the BCP 00302 authorization in NMOS systems specification. We have also implemented the IS-12 control protocol, which includes implementation of the MS-0501 NMOS control architecture specification and the MS-0502 NMOS control framework specification. Coming soon to the code are the following: an implementation of the BCP 00303 certificate provisioning specification that we've developed for the automatic management of digital certificates. An IS-11 stream compatibility management implementation has been developed by Macnica. The IS-11 specification provides a mechanism to configure senders using information from receivers. An IS-13 NMOS annotation specification implementation is being worked on by NVIDIA. IS-13 specifies how to update resource annotations in an NMOS system. The IS-13 specification is still a work in progress, but hopefully this implementation will be ready soon after the specification is published. And finally, the IS-14 NMOS device configuration specification, which is also a work in progress. We plan to implement this once the specification has been published. To give a little more detail about those recent additions to NMOS CPP, let's start with IS-10 and BCP 00302, which are the NMOS authorization specifications. These are based around OAuth 2, which is an industry standard for authorization. The OAuth standard is itself based on best practices and standards from the Internet Engineering Task Force and OpenID. Within OAuth, there are several authorization workflows, but the two recommended by the NMOS specifications are authorization code flow, which is where a user provides a username and password. This is for devices or services with a user interface. The other is the client credentials flow, where a device can authenticate without the need for entering a username and password. This is for devices or services without a user interface. Sony were actively engaged in the development of the NMOS authorization specifications. And you can catch up on YouTube with the presentation we did previously on this topic at the AIMS IP Oktoberfest called Underpinning the Pyramid: Security in NMOS Systems. Sony are first to provide an open source implementation of the NMOS security specifications to the industry. Our implementation supports the authorization code flow for nodes with a user interface and the client credentials flow for nodes without a user interface. Our implementation also provides support for private key JSON Web Token to provide an extra level of security. Moving on now to the NMOS control specifications. Firstly, let's explain a bit about the MS-05 and IS-12 specifications. The MS-0501 and MS-0502 specifications define an architecture for modeling the structure and functions of an NMOS node. The resulting model is called the device model. The IS-12 specification defines a WebSocket-based control protocol for interacting with that device model. The separation of the model specifications from the control protocol specifications means that in future we can define other ways of interacting with the device model. In fact, I've mentioned IS-14, which is a work-in-progress specification for device configuration, and as part of this work we are defining a RESTful HTTP interface to the MSO5 device model. Sony have been actively engaged in the development of the control specifications and have been responsible for authoring the NMOS testing compliance test suites. There are two test suites that will soon be merged with the NMOS testing tools open source. The test suites offer different levels of testing, which when used together ensure a comprehensive test of the device model. We've also implemented the complete MSO5 and IS-12 specifications as part of this NMOS CPP open source software. Let's dive a little deeper into the MSO5 device model. The device model is a hierarchical tree structure constructed from objects instantiated from class definitions. The structure of the device model is flexible and is determined by the implementer of the NMOS node by defining the structure of the device model in their application code. Each object in the device model contains properties and methods. The properties are values that model the state of the NMOS node. Examples might be status variables reflecting the connection state of a receiver or configuration parameters. The methods expose functions of the NMOS node over the control interface. Changes to properties in the device model generate property change events, which we'll return to a bit later. When an IS-12 client connects to an NMOS node, it has no prior knowledge of the structure of the device model or of the objects and data types that are used to compose the model. The device model is self-describing, which means the IS-12 client can be generic. The client queries the node for the structure of the device model and also queries for the class and data type definitions. The device model has a class manager, and this can be queried for class and data type definitions. Here we've illustrated an IS-12 client connected to an NMOS node via a WebSocket using the node's IS-12 API. The client can get and set properties on the device model, and it can also invoke methods exposed to the control interface by the device model. The NMOS node application code can get and set properties on the device model. Methods called by the client on the device model can call back into the NMOS node application code so that those methods can be performed by the node. Similarly, if any property value changes on the device model, these changes are reported via a callback to the node application code. Clients can subscribe to objects within the device model so that if the value of properties in that object are changed, for instance by the NMOS node application code, then it will generate a property change event. Property change event is then transmitted over the WebSocket to the client. Going back to the structure of the device model, there are three types of objects that make up the device model: blocks, workers, and managers. A block object is a container for child objects, for instance, the root of the device model. In this example device model, we also have a sender block that contains the sender objects and a receiver block that contains the receiver objects. Next, we have worker objects, which represent a component or function of an NMOS node. In this example device model, the senders and receivers of the NMOS node are modeled as worker objects. Finally, we have manager objects, which are singleton objects that represent housekeeping functions. In this example device model, we have a class manager and a device manager. The class definitions in MSO5 are object-oriented and therefore exhibit inheritance, and the relationship between the classes can be seen in the MSO5 control model. The MSO5 control model defines the objects we can use to build our device model. The control model classes are defined in the MSO502 specification, but there are also domain-specific classes and data types that are defined in the NMOS feature set register, which we'll return to a little later. These classes are referred to as standard classes and standard data types. Classes and data types are expressed as descriptors that define their structure and attributes, and we can see a couple of examples on this slide. Vendors can implement their own application-specific classes and data types. These are referred to as non-standard classes and non-standard data types. Returning to the MSO5 control model and thinking about the classes in our example device model, the standard classes are shown in orange, and here in blue are the user-defined non-standard classes that have been added that derive from the worker base class. Expanding a little more on the manager objects in the device model, the class manager handles class and type discovery. Every device model must have one and only one class manager, and the class manager can be used to query for control classes and data types. The device manager contains basic device information and statuses. The device model must have one and only one device manager. Device manager can be queried for manufacturer and product specific information such as product name or serial number. The NMOS feature set register defines domain specific classes and data types, where each feature set defines classes and data types for specific use cases. Feature sets can be added to the register without the need to update the NMOS specifications. At the time of this presentation, there were two feature sets in the register, for identification and monitoring. The identification feature set can be used to model a tally light, and a basic monitoring feature set can be used for modeling connection and payload statuses for stream receivers. Current works in progress that will add to the feature set register in the coming months include the device configuration feature set and the status reporting feature set. The device configuration activity, called IS14, is defining classes and data types for retrieving and restoring device configurations. The status reporting activity aims to enhance the existing monitoring feature set to give a richer set of status monitoring and reporting functions. Let's consider the user benefits of MSO5 and IS12 and why it's worth using for device control. Firstly, it's ready now. The specifications were published in September 2023, and the NMOS CPP implementation is ready to be downloaded and used. Once the device configuration and status monitoring activities are completed, these will be added to the NMOS CPP implementation, making those functions available also. IS12 is secure as standard. It uses NMOS BCP 00301 for transport layer security, and IS10 and BCP 00302 for authorization. It is also supported by compliance tests in the NMOS testing tool, where the IS12 test suites are soon to be merged. This means that you can easily check that your device model complies with the specification, helping to ensure interoperability. Let's move now to the NMOS CPP implementation of MSO5 and IS12. We've implemented the entire MSO5 and IS12 specifications. This includes implementing all standard classes and data types defined in the MSO5 specifications and all those currently defined in the NMOS feature sets register. Within the codebase, we provided helper functions to allow easy creation of device models and also examples of how to create user-defined non-standard classes and data types. Let's see how we can define a simple device model using the NMOS CPP code. Firstly, we define a root block. Next, we create a device manager and a class manager. Now we're going to create a block for our channel gain controls. Then we make the gain control objects using a user-defined helper function. We'll dig into that in a bit more detail in a moment. Finally, we add the device model into the NMOS CPP resource model. Let's expand on that user-defined helper function. When we define a user-defined non-standard class, we first need to define the class descriptor. First, we define a class ID, and because this is going to be a worker class, we inherit from the worker class ID. Next, we define the class descriptor and its properties, and we insert the class descriptor into the framework. Now we've defined the class, we need a function to instantiate it. Within this function, we first instantiate the worker base class and then instantiate the class properties. This is a simple example, but in the codebase, there are many examples of defining and instantiating different types of non-standard classes and data types. This is in addition to the helper functions for instantiating all the standard classes and standard data types. In summary, what's new in NMOS CPP? IS10 authorization is ready now and available. IS12 control is also ready and available. It's secure as standard using BCP 00301 transport layer security and IS10 and BCP 00302 authorization. All of this is supported by compliance test suites and the NMOS testing tool to help ensure interoperability. Many thanks for listening.